Hello, welcome to another Digital Control Systems Technology lesson. In today's lecture, we are going to be looking at microcontrollers or hardware-software co-design, how we can bring in both hardware and software components into building digital control systems. And we will be specifically focusing on microcontrollers in today's lesson. So when we talk about microcontrollers, you would have already studied about microprocessors in one of the previous modules, such as computer architecture, computer systems organizations, and so on. When it comes to microcontrollers, they are again integrated circuits, chips, but they are designed specifically for the purposes of embedded applications. Not limited to embedded applications, but that's a prominent application that they would be used. And the main differentiation that we would see with microcontrollers and general microprocessors is they are going to have a microcontroller is going to include the processor, the microprocessor, and in addition to that microprocessor, it may also have some memory and also some input-output capabilities. So because we have these three components, and from your understanding of a general purpose computer or the von Neumann architecture computers, these three form the main part of a computer: the processor, the memory, and input-output. So what we essentially get from a microcontroller is we get a computer. So there may be certain limitations. For example, we may get a microcontroller, it may be an 8-bit, 16-bit, 32-bit, or even sometimes a 64-bit microprocessor inside that microcontroller. But that is what we are going to get. Then, in terms of memory, also, it would be fairly common for us to observe that most microcontrollers may have limited amount of memory when comparing to general purpose computers. Then another thing that we may observe is, depending on the expected application of a microcontroller, it may support certain input-output peripherals, certain input-output connectivities, and not the other ones. So we may have some of these limitations in terms of what is the processor, what is the memory, what is the input-output. But what we essentially get here is we get the three main components necessary for a computer. So with a microcontroller, we get a mini computer. Then from a software point of view, in most microcontroller environments, or rather in most situations where we would use microcontrollers, we may not go for the typical operating system option. So in a typical computer environment, we would have the computer hardware, and then we would have the operating system, on top of which we will run our application software. But with many microcontroller environments, it's most likely for us to go from high-level language that is converted into machine code and directly run the programs themselves. So we may run the programs directly without an operating system. So again, this is something that we would observe with many microcontroller environments. But the thing to remember is, these limitations are not like standards. There may be certain microcontrollers that may deviate from these general descriptions. But this is generally a way to identify a microcontroller, general properties or general capabilities of a microcontroller that we may come across. So as we said, a microcontroller is essentially a microprocessor with on-chip memories and input-output devices. So that is essentially what we have in a microcontroller. And compared to general purpose microprocessors, one of the things that we would see with microcontrollers is, in most scenarios, they would be designed for specific functions. Say, for example, we may get microcontrollers that are intended for digital control systems. We may get microcontrollers that are intended for audio devices, for video devices, for remote controllers, for mobile applications. So we may get microcontrollers for such specific applications. But even with specific applications, the reason why we may go for microcontrollers is because if we can find a microcontroller for that specific application, then it would become an all-in-one solution. So that is, we can just use that microcontroller and we don't have to have many chips. So we can reduce the amount of chips in our device because we already have the necessary memories and some input-output capabilities. So with this reduction in chip count, having an all-in-one solution, something that is designed for specific functionality, so it can do the things that we need for that particular function, we can get a number of advantages in terms of reduced cost. So because we don't need all the capabilities that we may assume for a general purpose application, we can limit the capability of this microcontroller to only what we need. For example, with a general purpose computer, it needs to run word processing software, it may need to run video players, it may need to run audio, so it has to cater to a lot of different things. Whereas in a microcontroller, if we design it for a specific function, then we can limit what it needs to do. Then we can have a device that can be manufactured at reduced cost. It would use reduced amount of power, and also physically we can reduce the size of the device that we are building. So for that reason, for many embedded applications, many digital control systems applications, we may tend to use microcontrollers. So it doesn't mean that we have to use microcontrollers. We can use microprocessors if that is what we need to do. In certain places we may do that as well, but microcontrollers will give a number of advantages like these. So when we think about where we may find microcontrollers, it is in a way around us a lot. So we would find microcontrollers in things like mobile phones, cameras, even washing machines, or a lot of household items, things like a set-top box for a television itself, a microwave oven. So these type of kitchen appliances, entertainment units, all of these things may use a microcontroller. Then we may even come across microcontrollers in sort of light applications, lighting and sensing, so automated lighting, temperature sensing applications like in air conditioners, fire detection, fire safety applications, fire alarm systems, things like that. Automobile devices like an braking system, fuel injection system, so these could be implemented in microcontrollers. So we would come across microcontrollers. If you look around yourself, there may be a number of devices that could have microcontrollers in them. Then when we go beyond a home environment, we can even find microcontrollers in a lot of industrial control applications. So industrial devices, process control devices, when we are building these digital control systems, many of the times we can build them, or the main core computational aspects of these digital control systems can be put in a microcontroller. Then we may even find these in things like metering measurement devices like voltmeters, current meters, a lot of these other handheld devices, a lot of embedded applications. We very commonly come across microcontrollers. So the main thing to remember is microcontrollers are very commonly used. So when we think about computing devices, computational devices, in a way we have more microcontrollers than we would have microprocessors, because microcontrollers are there in many simple smaller devices, and their adaptation and their usage is becoming more and more common these days with the advancement of things like Internet of Things, a lot of embedded systems, a lot of connected digital systems. So when we have such a situation, we have more and more microcontrollers being used around things that we would come across. Then the question is, why we want to use microcontrollers, or why we are studying microcontrollers in this module. One of the main reasons is, when we are trying to build digital control systems, particularly from the point of view of practicing that, from a prototyping point of view, trying out new things, using microcontrollers would be a very good approach. So it is very useful to build a lot of applications, particularly in the domain of digital control systems. In addition to that, you can use it to understand programming, understand the basics of computing, because they themselves replicate this typical computer model, and then also things like understanding compilers, security, and other topics as a general learning platform. Because microcontrollers are much cheaper, you can get access to them in a much easier way. So it could be a useful tool as a study tool as well. But generally in digital control systems realm, there's a great amount of use, great amount of application of microcontrollers when we are building such systems. Even as part of this project, you will be building your final project for this module using microcontroller based systems. Then when we think about classifying microcontrollers, because microcontrollers are going to have the basic components of a computer, all the classifications that we could have for those computers can also be had for microcontrollers. So when you were studying computer architecture, you would have studied certain ways of classifying the computer, classifying microprocessors, classifying memories. Those things can also translate into how we classify microcontrollers. So for example, we can classify them according to the bit number, like 8-bit microcontrollers, 16-bit microcontrollers, or 32-bit microcontrollers, or even sometimes 64-bit microcontrollers. But one of the things that you may see here is, compared to general purpose processors, say for example, presently most of the computers that we would get are mostly 64-bit microprocessors. They would use 64-bit microprocessors. But still, most of the microcontrollers that we may use will be 32 or even 16-bit microcontrollers. Even in some applications, 8-bit microcontrollers are commonplace, but mostly 16 or 32-bit microcontrollers are still fairly common. The reason being, because we are not targeting for a general computing application, many of the microcontrollers, many of their capabilities are good enough for the limited applications, limited functionality we need, even with lesser capable microcontrollers or microprocessors inside them. So For a general purpose computing application, we may need 64-bit computing, but some limited functionality microcontroller application, a 64-bit microcontroller, or rather a 16-bit microcontroller, would be good enough. And using that, we could get a lot of cost saving and so on as well. So there is a lot of reasons why we may go with these various microcontrollers. Then another way that we may classify microcontrollers is using the type of memory devices that we can have. We said most microcontrollers will have embedded memory or will have some memory included in them. So if we have embedded memory or if we have memory included in them, we would call that embedded memory microcontrollers. Whereas if we can connect extra memory outside of the microcontroller, then we may call that external memory microcontroller. So depending on the internal architecture, sometimes we may get microcontrollers that may not have internal memory. Sometimes they may have some internal memory, but we can interface more external memory into the same microcontroller to extend the available amount of memory. So we can have these variations as well. Then in terms of the memory architecture, so again, if you recall from your computer architecture lessons, we can classify computers based on the memory architecture in terms of whether we have a single memory architecture for both program memory and data memory, or we use separate memory allocations for data memory and program memory. So the Harvard memory architecture, where we use separate program and data memory, and the Princeton memory architecture, where we use the common memory address scheme for both program and data memory. So this memory architecture can also be there in a microcontroller. We can use any one of these memory architectures in our microcontrollers as well. Then another classification that we would come across is again something that you would have studied in computer architecture about instruction set architectures. So whether we can use complex instruction sets or reduced instruction set. If we use CISC or a complex instruction set architecture, we can use much longer, much complex instructions, but it would be simpler for programming. And if you use reduced instruction set architecture, we have to use many different instructions to achieve the same outcome, but we would have more simpler instructions. So again, if you recall your knowledge on CISC computers or complex instruction set computers, there we would have a full set of instructions. So programmers can do programming much easily, but each program instruction might take multiple cycles, multiple clock cycles. On an alternative point, in reduced instruction set computers, they will have limited amount of instructions implemented, so you may have to do a bit more programming. But particularly when we think about microcontrollers, it is most commonplace for us to have RISC architecture microcontrollers because they have limited amount of instructions, so they can be much simpler in terms of the hardware. They can be much smaller in terms of size. They can be less in terms of their power consumption. So when we think about all these mobile or embedded type applications, things like ARM architecture, ARM processors, ARM microcontrollers, we would see that reduced instruction set computers or RISC computers are fairly common in microcontroller environments. But the general principles with CISC and RISC are the same as what you have studied in computer architecture, but you may refer to some of these online resources to get a bit more idea about these if you want to do a revision on that. So once we have the hardware component, once we have the hardware component of a microcontroller, which is having the microprocessor, memory, and input-output devices, now the next thing that we need to do is the software aspect of it. We need to program the microcontroller. We have to write a program code and put it on the microcontroller. The typical way we would go about doing that is we would write the program on a computer, compile the program for that particular instruction set of the microprocessor inside the microcontroller. So depending on what microcontroller we are using, there would be a particular instruction set architecture. For that particular instruction set architecture, we would compile the program, and then the compiled program could be loaded onto the microcontroller, and then that microcontroller can be used. Then when we think about programming these microcontrollers, again, the same principles of programming microprocessors would apply. So we can use the low-level machine code to program, where we would be programming in binary, but it is more obscure and complex for software development purposes, where we are programming at the instruction set level in machine code. But we would ideally use what is called the assembly language. So it is again a low-level programming approach, again something you would have studied in computer architecture, but we can use the same approach in programming microcontrollers. Each microcontroller would have its own instruction set architecture, the set of instructions that it would support based on the family of processors that it has, and based on that we can program in an assembly language which is much more human readable instructions. So we will have things like add, multiply, and things like more human readable instructions, and we would use that to program, and then we would use assemblers to convert them into machine code. So that is a way that we would use assembly language programming. But one of the most suitable approach from a programmer's point of view is using high-level programming languages, because with high-level programming languages we can program in a more easier manner. It is much easier to manage and understand, read and write code, and when multiple people are working on programs it would be much easier. So the same principles about why high-level programming is much more preferred than, say, assembly language programming or machine languages. Because of the ease of use, we may use high-level programming languages and then use compilers to compile them into that specific hardware. In the case of microcontrollers, compiling to the particular processor architecture of the microcontroller. So that is how we would basically program microcontrollers, not that different from how we program general purpose microprocessors in general purpose computing. Now let's look at some common types of microcontrollers that you may come across. We are not going into details of each specifics of different microcontrollers. That you will have to choose depending on what you are building as a digital control system for your particular system that you are developing. You may use some microcontrollers for prototyping, some for final development and things like that. So that is not in the scope of this module, but we are looking at some different types, different options that you would have when you need to do microcontroller based development. So one of the earlier microcontrollers that came about was the 8051 microcontroller, which was developed by Intel in the 80s, and it had a CISC architecture with a complex instruction set computer with a Harvard memory architecture. But later on, what we would observe is most of the other later microcontrollers switch to having RISC instruction set architectures, and because they were much more efficient when building low cost power efficient devices. So PIC microcontroller is a fairly common microcontroller. It's pretty cheap. You can get them for like the cost is pretty cheap, and you may find them heavily used in simple electronic implementations, light displays, a lot of these simpler implementation still using PIC microcontrollers. Then we have AVR microcontrollers, again another RISC architecture microcontrollers. They are much faster. So one of the issues with PIC microcontrollers is they are very low cost, they are available widely, but they are not that efficient, they are not that fast in terms of their computation. So you can't build a lot of complex tasks or complex systems using PIC microcontrollers, whereas AVR microcontrollers compared to 8051 or the PIC microcontroller families there are much faster variants available in that. An example of an AVR microcontroller is ATmega328, which is a fairly commonly found microcontroller and when you go about picking a suitable microcontroller, some of the things that you would look at is what is the program memory available. Say that is the amount of program code that you can put. So once you write the code and compile, this is the total amount of memory that you can use for your program. Then in addition to that, if you are executing different data, different instructions, different data that you need to process, then again there will be additional data memory. Again, you will have to think about that, whether this data memory is enough for your instructions. The data memory can be available in few different forms, sometimes as EEPROMs, that is electrically programmable, erasable programmable memories, or SRAMs, static RAMs. So again, you have to think about the available memory. So it is like thinking about what is the hardware side, hard disk storage and the RAM of a computer. So you would think about that in terms of what is the memory that we would have to put the program, what is the data memory for running these instructions. Then we would also think about how many input output pins we have and how we can interface this with different components. Say when we are building digital control systems, we would interface these microcontrollers with different sensors and things like that. So then if you want to connect this to different sensors, displays, input, output, buttons and things like that, we need to have enough connectivity to connect them. Then in addition to that, we will have other computational components like timers, analog to digital converters, sometimes like pulse width modulation components, so we will have various different components like that, which we will consider whether that is suited for our particular application. So when we are choosing a microcontroller, this is just an example, but we will look at these examples or look at the available microcontrollers and choose based on the specifications to see if that is suitable for our applications or whether it is not suited. Then one of the common ways that you would use microcontrollers, particularly from the point of view of prototyping and developing systems, is not using just the microcontrollers but using them in a prototyping platform. So one of the common and popular prototyping platform that you would come across is the Arduino platform, and that is the one that we would be using as part of this course for your projects and so on. And with Arduino platform, what you have is it is an open source prototyping platform which includes the Arduino hardwares, the hardware boards, which would include the microcontroller and various other components. Say for example, it would include the microcontroller chip and then also various other connectivities, power supplies and all these things. So you just don't get the chip and then you have to build all the electronic components. You get many of the other electronic components to straight away start building things. So that is the idea of these prototyping platforms. So you will get those hardware boards. Then with Arduino, you also have a programming language which is fairly similar to C programming, but a modified version of that, or extended version of that, so to speak. And then also a software development tool, an IDE, an integrated development tool, on which you can develop your program. Then you can load it onto a microcontroller connected to that computer microcontroller board, and then you can test out your application. So the reason why we will be using the Arduino platform for our course is that it is much easier to access a microcontroller that way. So rather than us having just the microcontroller chip and trying to build all the all the other electronic components, and it is pretty inexpensive, particularly the Arduino platform. Most of the microcontrollers we would get with that are pretty inexpensive and easy to get on. So as part of this course, you have already been given the project task. So we will be building that using Arduino platform, and you can get some more details about Arduino platforms through some of the additional resources shared as well. So one of the things that you would find with Arduino boards also is that there's a lot of variation with them. So there are many variations with different processors, different input-output capabilities, different storage capabilities, the amount of storage, amount of RAM, all these things may differ, and different connectivity capabilities. So you will consider these variations when you are building your system. So if you want to build a particular digital control system and you need a certain amount of analog input-output, say for example, if you need a fairly higher number of analog input-output, you may have to go with something like the Mega board. If you don't need a lot of analog input-outputs, you can go with something that has less number of analog inputs. So you would think about those as well when you are going with or going about choosing a development board for your projects. So just as an example, so again, not to go into the specific details, the main things that you would go about these Arduino Uno boards, which are the ones that you would get to build your projects as part of this course, many things that you would observe is like the USB connectivities, the power connectivities, various like power lines like ground lines, power supply in terms of 5-volt power supplies, 3.3-volt power supplies, then a range of analog pins that are available there. So these analog pins can be used if that is necessary. So you will have some analog pins. Then you will have a number of digital pins. So again, you can use them with things like pulse width modulation and things like that. So as digital input output. Then you will have some other buttons, LED displays, and so on. So this is a general idea of a development board, a microcontroller development board that you would be using as part of this course. And when you go about using them, the main thing that you would have to figure out is using a pinout diagram to figure out what each pins mean, what things you can connect to these pins, which are the power inputs, which are the power outputs, which are the digital inputs, which are the analog inputs. So these are the things that you will have to figure out and use. So from a course point of view, we are not going to details about each of the various microcontroller boards that you can come across. That you will have to study on your own, and you can find resources online, and you can easily find out these pinout diagrams and things like that and learn about those. But we are just covering the general principles here. Then particularly with Arduino, we also have Arduino IDE where we use the term of Arduino sketches, which are the programs that we write in the Arduino language, and then we can run those in the Arduino boards. So this language is pretty similar to C programming, and which you have done previously, I guess. And then, so for you all, this would be fairly easier. And there are a lot of online resources that you can use to learn about Arduinos, a lot of online tutorials, a lot of video tutorials. So please go and refer to some of these resources. They are pretty useful for you all in this course perspective, particularly when you are trying to build your project component of this course. And finally, even when you don't have access to the hardware components of Arduino or microcontroller boards, there's always the possibility of using simulations. So you can use the various simulation tools such as Proteus or online tools like Tinkercad. So you can use these tools to simulate Arduino boards and build your system. So it is not a limitation that you don't have a hardware board. There's always many different online tools with simulations where you can try out these things. You can test before build, which is a good approach as well. So you don't commit to your hardware design before you know that hardware design is good. So you can start with your design, then you test your design in simulators. So before you can actually build that, so you can verify whether the design is good. So then you can save money and time in wrong designs at the hardware level, and then you can go about building the system in the hardware case. So in your project scenario also, it would be a good idea to start with your project designs in simulation environments, and then we would see how we can progress onto hardware based building. So that brings us to the end of the main lesson today, and a reminder about your project design. So your project design and the submission that you will have to do is already available on LMS, and number of instructions relevant to that has already been shared. And what we have covered today about simulations and using online or simulation tools to design your Arduino based control systems, Arduino based systems, is what is expected as part of this design phase of your project. So you need to do a project design using one of these tools, incorporate the other elements of your project, other sensors and other components of your project, and incorporate all of these things into that design document, and that is what you will have to submit as part of your group projects. So if you have any questions about the things that we have covered today, or any questions about your project design, you can always reach out to me using your usual communication channels of LMS or email or messaging. Anything would be fine. So please make sure you clarify all your questions about project design, Arduino boards and all these things before the the submission deadline for your project design. And as always, if you have any concerns, if you have any questions, feel free to raise with me so we can have a think about what are the alternative ways we can go about working on this project as part of this course. So with that, that's all for today. See you next time in the next lesson. Thank you for joining, and bye.